In this video, we look at an actual diode and also talk about the main difference between an actual diode and an ideal diode. And I mentioned this in an earlier video that the primary difference between the actual case and the ideal case is that when you have an actual diode that's forward biased, the voltage across that forward bias diode will not be 0 volts like the ideal case. In the reverse bias situation, ideally you have 0 current, and in the actual case the reverse bias current is not 0, but it's so small that in most cases for all practical purposes you can just assume it's 0. So really there's little difference in the actual and ideal reverse bias case, at least in most situations. So the primary difference is what happens in the forward bias case with the forward bias voltage. So the amount of voltage that you'll have across an actual forward bias diode depends primarily on the material that it's made out of. Silicon, as I mentioned before, will have a forward bias voltage between 0.6 volts and 0.7 volts. Germanium will have a couple tenths of volts, usually in the range of 0.2 to 0.3 dropped across it when it's forward bias. And then gallium arsenide, another semiconductor that sometimes is used, has approximately a 1 volt forward bias voltage drop. Okay, so let's look at why we get this relatively small amount of voltage across a forward bias diode, and to do so you have to look at the physics that happens at the junction of the diode. Remember, a diode is made by putting some p-dope material together with some n-dope material and forming a junction. So here again is the p-n junction that I talked about in the very first video on diodes, and here is the diode symbol. Remember that the anode side of the diode corresponds with the p side of the junction, and the cathode side of the diode corresponds with the n side of the junction. So you can see in this circuit that we have a forward bias diode, since the higher voltage Vs here is connected to the anode and the lower side of the source is connected to the cathode. Again, this isn't a practical circuit because we don't have any resistance in the path where the diode is, so you don't actually want to hook a diode up like this because you would actually overheat it, but we'll see what occurs when we have resistors along with the diode and sources when we get to problems of actual diodes coming up in a future video. Okay, but I just kept this as simple as possible because we're just looking at it conceptually here. So this diagram above my circuit, this is zooming in on the p-n junction. So here on the n side, these pluses with a circle around them represent positive ions, and the red minus signs represent free electrons. And then over here on the p side, the minuses with the circles around represent negative ions, and the green pluses represent free positive charges. Now I have another diagram here that shows what I'm depicting with the on the n side, with the red minus signs and the pluses with circles around them in more detail. See, this is a picture of n-doped silicon, okay, where the plus 4, these are, or this is the nucleus, so you have 4 protons in the nucleus of a silicon atom, and then these 4 black dots are the valence electrons in the outermost orbit. So these silicon atoms, as you can see here, are electrically neutral, and to make an n-doped semiconductor, as you learned in chemistry, you add a substance that has 1 more valence electron than this than the semiconductor material has. So a common material that's used with silicon is phosphorus. So here's a phosphorus atom with the 5 protons. 4 of the 5 valence electrons of the phosphorus atom pair up with neighboring silicon valence electrons, and they make these covalent bonds. But the extra valence electron of the phosphorus doesn't have a neighboring valence electron of a silicon atom to pair up with, so it becomes free, it's unbounded, it's not bonded, and this is the charge that can contribute to a current and effectively reduces the conductivity of the silicon. Okay, so in my diagram, the red minus represents one of these free electrons, and the plus with the circle around it represents one of these phosphorus atoms, which is a positive ion, since it has a net positive charge, because as you can see, it's got more protons in the nucleus than what it has for valence electrons. So that's the N side. The P side is just that now when you add a substance to the silicon, and boron is a common P dopant, well, now what occurs is that you have the boron, which has one less valence electron than the silicon. So the three valence electrons pair up with neighboring silicon atoms, and then a valence electron from a silicon atom will actually drop into the valence orbit of the boron, and that's because the boron valence electrons are at a lower energy level than what the silicon valence electrons are at. So what occurs is that now you have a negative ion, because you're going to have 4 valence electrons and only 3 protons in the nucleus for the boron, which is called the acceptor atom. And then you'll have a positive charge, a valence electron position here that's empty, which is your positive free charge that can contribute to a current and reduces the conductivity of the semiconductor. Okay, so that's just a little better explanation of what this diagram shows. Alright, so what occurs? Well, what occurs here right at the junction is that these free electrons are in close enough proximity to the free positive charges, the holes, that they recombine. Okay, they do what's called recombination, which means the electrons just fill these holes. And this only happens in close proximity to the junction, because the distance between those unlike charges, which generates an attractive force, well, there's a strong enough attractive force over that small distance that the recombination can take place. So, this electron here will recombine with this positive charge. This electron, say, fills this hole. This electron here fills that hole. This electron here fills that hole. But then these free charges, far enough away from the junction where the attractive force is not strong enough for the recombination to take place, well, they just stay where they're at. They don't fill these holes over here. So what you end up with is you have a region, okay, that's in close proximity to the junction, the p-n junction. Oops, that wasn't very straight. Okay, but you see you'll have this region here which is depleted of free charges, and it's called the depletion region for that reason, that it's depleted of any free charges. See, all that you have in this depletion region are positive ions. Okay, there are no free positive charges. So on the N side of the junction, you have a net positive charge, okay, since there's only positive ions. And on the P side, you have a net negative charge, since there's only negative ions on that side of the junction in close proximity. And anytime you have a separation of charge like this, well, there's a voltage that's across where you have a separation of charge. So you see, you get this voltage across the depletion region. And remember from your circuits that you can think of voltage as pressure, like pressure in a hydraulic system. So you can think of this voltage across the depletion region as an internal pressure that the diode has. So in order to get current to flow in a circuit through a diode, you first have to overcome that internal pressure. And you know, that's what this external source will do. That when this external source um, is at an appropriate level, well, it will effectively overcome that internal pressure and current will start to flow. Now, the barrier is over, well, this voltage, I forgot to put here, but this voltage that's across the depletion region, it's called the electric potential barrier. All right, so you see these voltages across the diodes that we get when they're forward bias, that's the amount of voltage that's needed to overcome that barrier. You know, remember, voltage is an indication of amount of energy that's needed to move charge between two points in a circuit or two nodes in a circuit. So before current will freely flow through a forward bias diode, it has to overcome this internal pressure, okay, this electric potential barrier. Now, the way it's overcome is in an exponential type of fashion. Okay, it's not a linear type relationship, and it's not like you know, no current will flow at all until that barrier is completely overcome, and then you know, current will flow completely unimpeded, other than the resistance that's in the path of the diode. It's an exponential type of way that this barrier is overcome by this external voltage that we apply. And we'll specifically look at the IV relationship of an actual diode and compare it to the ideal case, and then start to solve some problems where we're considering the diode to be actual. Okay, but this was just the physics behind why we get this relatively small amount of forward bias voltage across a forward bias diode. You see, in the ideal case, you pretend that this depletion region doesn't exist. Okay, and if the depletion region doesn't exist, well, there's no barrier that you first have to overcome, and that's why we say that there's 0 volts dropped across an ideal diode that's forward bias.